I, Vinita Philip, Assistant Professor of the Department of Electronics and Telecommunication Engineering, AISSMS, Institute of Information Technology, present my video on the topic Algorithms for Efficient Computation of DFT. The computationally efficient algorithm for DFT is made possible by using FFT. Divide and conquer approach is used in the development of computationally efficient algorithm, namely FFT algorithm. As the name suggests, this approach is based on splitting of n-point DFT computations into two n by 2 point DFT computations. Each n by 2 point DFT is further split into computations of 2 n by 4 point DFT, and so on until we are left with a 2-point DFT. There are two FFT algorithms. DIF FFT uses decimation in frequency approach, and DIT FFT uses decimation in time approach. In this video, I would be illustrating the first algorithm, that is DIF FFT algorithm, using a numerical example to a case when n equal to 4. DIF FFT algorithm. Step number 1 of the algorithm is that we need to divide the input sequence containing n number of points into two parts. One containing samples from x of 0 to x of n by 2 minus 1, and the other containing samples from x of n by 2 to x of n minus 1. For n equal to 4, we divide as x of 0, x of 1 and x of 2, x of 3. The next step of the algorithm is to decimate the DFT output, that is decimation in frequency. We will separate the even coefficients and the odd coefficients. Let us represent the even coefficients by 2k and the odd coefficients by 2k plus 1. So to find x of k for k even, we need to take DFT of g of n, and g of n is given as x of n plus x of n plus n by 2. When n is equal to 4, g of n becomes x of n plus x of n plus 2. Substituting n equal to 0 in g of n, we get g of 0 is equal to x of 0 plus x of 2. And substituting n equal to 1 in g of n, we get g of 1 equal to x of 1 plus x of 3. Now to find x of k for k odd, we need to find DFT of h of n. And h of n is as given in this formula. For n equal to 4, when we substitute n equal to 0 in h of n, we get h of 0, and when we substitute n equal to 1, we get h of 1. Step number 2 of the algorithm is demonstrated on a flow graph as seen. The last and the final step of this algorithm is that when n is equal to 2, we need to compute n by 2 point DFT, which is a 2-point DFT. It is also called as butterfly computation. So to compute even coefficient of DFT, that is x of 2k, we add x of n and x of n plus 1. To compute odd DFT coefficient, we subtract x of n plus 1 from x of n. The final signal flow graph for n equal to 4 for a DIF FFT algorithm is as seen. Let us now use a numerical to demonstrate this algorithm. Given that x of n is 1, 2, 3, 4, let us use DIF-FFT algorithm to find x of k. The signal value at this point is obtained by adding x of 0 and x of 2, which is 1 plus 3 equal to 4. At this point, x of 1 plus x of 3, which is 2 plus 4, which is 6. At this point, x of 0 minus x of 2. So 1 minus 3 is minus 2. And here it is x of 1 minus x of 3, which is 2 minus 4, which is minus 2. The same signal values go as the input to a 2-point DFT, except for the last row, wherein we need to multiply this value with minus g. So here we get is plus 2g. The final DFT output x of 0 is 4 plus 6 by computing a butterfly computation, that is 10. X of 2 is 4 minus 6, which is minus 2. X of 1 is minus 2 plus 2j, and x of 3 is minus 2 minus 2j. We see that output DFT coefficients are not in proper order. We have to change the position of DFT coefficients obtained so that it is in proper order. We observe the complex conjugate property in correct order of coefficients. To conclude, the algorithm was explained with a numerical computation directly on the flow graph. In the subsequent video, I would be discussing the DIT-FFT algorithm. So that's all for now. Till then, stay tuned. Thank you for watching.